The following episode is brought to you by the American Urological Association. This episode comes to you from the AUA 2024 plenary.
It is now my distinct privilege to introduce our next speaker, Craig Niederberger. Craig, is you going to come from one direction or the other? Dave's going to bring him on stage. Dr. Niederberger is this year going to give the Ramon Guiteras Lecture. Dr. Guiteras was one of the very early innovators and pioneers of the American Urological Association. And it is actually a very significant honor to be invited by the American Urological Association to give this presentation. Dr. Niederberger is professor and the Clarence Seelhoff Chair of and the head of the Department of Urology at the University of Illinois at Chicago College of Medicine, and he's also notably a professor of bioengineering. Dr. Niederberger every year has not one but two PhD graduate students in computational science working in his laboratory. And what he's going to talk about today is a bit of what I mentioned in my presentation. The title of this is Modern Innovation, Promise or Peril? And Craig, very much looking forward to hearing what you have to say. Welcome to the podium. It's a well-deserved honor. And it's great to see you.
Good morning. Thank you, Dr. Meacham. Thank you to the AUA leadership for this really wonderful honor. And thank you to all of you for coming in early this morning to hear about modern innovation. So when I was asked to give this talk, the theme presented was there are technologies that people are worried about, and can you address them, such as ChatGPT. So I said, sure, absolutely. I can talk about ChatGPT. But what's going on right now in innovation is remarkable. The barrier to entry to make incredibly sophisticated technological solutions in your home office is near zero. And we're teaching students of various kinds how to do innovation. And so we're in this moment of time where innovation is really easy to achieve. And I really wanted to talk about that as well. So here we are. And for those of you who are Star Wars fans, may the 4th be with you.
Oh, I get it.
These are my disclosures. Yeah, thanks. Okay, so the story begins, I think, with the creation of the modern-day computer. And there are really two heroes to this story. The inventor of software, and that's Ada Lovelace, the daughter of Lord Byron, and Charles Babbage, both brilliant computer scientists, both brilliant mathematicians. They created the field of computer science. They created hardware and software. So the story begins with Babbage in the early to mid 19th century in England, coming up with a device that would solve a problem that engineers were having at the time, and that was to have good, accurate tables of logarithms. And if you, probably most of you in this room aren't aware of this thing called long division, but if you are, it was like the bane of like elementary and junior high school. It was just such a pain, and it was so easy to screw it up. And that's exactly what making logarithms were, tables of logarithms. It was like long division on steroids, prone to inaccuracy, hard to do, but absolutely essential to make the machines for the Industrial Revolution. So Babbage came up with a device that he called the difference engine. And the difference engine was a device that would calculate, a mechanical device that would calculate tables of logarithms. And this thing would work. We know because there are two existing difference engines. Called it the difference engine because it uses the method of differences in order to calculate logarithms. One is in the Science Museum in London, and the other is in the Computer History Museum, or was actually until about 2016, in Palo Alto. And the one in London, they pull out every once in a while to special occasions to show that it works. The one in the Computer History Museum was there until 2016, and the docents there every hour would turn the thing on, and you could see it working. It was absolutely magnificent. But unfortunately, at the time, Babbage's compatriots, the technicians in England, were unable to make this difference engine. It was just too complex. Interestingly enough, the Swiss did. We know the Swiss did. We have a lack of historical information on Babbage. He didn't write much. Much wasn't written about him. So we know that the Swiss had made a difference engine which worked, and it was in the Crystal Palace, basically the World Fair, at the time of Babbage's life. So we can imagine that Babbage saw his creation working, knowing that his countrymen couldn't make it. So the government put a lot of resources into it, tried, and it was unable to succeed. Babbage actually designed another difference engine, 2.0 so to speak, with 1/3 of the parts, and it too would work, but that never was built, couldn't be built. And so Babbage did something quite remarkable. What he did was embark on creating an even more complex machine, which he called the analytical engine. And the analytical engine was a multi-purpose computer. It had this rotating drum with various arithmetic operations, and you could program the thing. The input was the punched cards that were used for textiles, to make textiles at that point, and that survived well into the 1970s, actually, these punched cards. It had output in the whole thing. It literally, Babbage invented the modern computer. This thing sitting in front of me, this thing in all of your pockets, that was invented by Charles Babbage. But of course, he knew that he could never make it. If he couldn't make the difference engine, he could never make this imaginary multi-purpose computer that would work. We don't have its design. What we have are notes about it, because Babbage really didn't write much. So in 1840, there was a presentation by Babbage at the University of Turin. And in the audience was a brilliant Italian mathematician, Luigi Menabrea, who took notes of the lecture in French. Menabrea actually would later become a prime minister. Simone Crivogliaro tells me that Menabrea is an Italian beer. So if you can find it, raise a toast to the guy who made the cell phone in your pocket possible. So Menabrea wrote these notes in French, and this is what we have as history of the analytical engine. And a friend of Babbage's, Charles Wheatstone, suggested that this brilliant mathematician, Lord Byron's daughter, Ada, translate to English, which she did. But what Ada did was she added notes to her translation. And the notes are 3 times as voluminous as the translation itself. And the notes are just absolutely wonderful, absolutely brilliant. So in Appendix G, she makes the first computer program for an imaginary machine. And this computer program would work on this imaginary machine. We know it's mathematically consistent, it's computationally consistent. So not only does she make the first computer program, it includes recursive logic, which is a fairly advanced computer science concept. So not only did she invent modern software, she really invented computer science. This is one of the most brilliant contributions to history, to technological history, and that's Lady Ada. So what she did was she wrote about it. And I think that this is very prescient for thinking about things like ChatGPT. She wrote, "It is desirable to guard against the possibility of exaggerated ideas that might arise as to the powers of the analytical engine. The analytical engine has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. It can follow analysis, but it has no power of anticipating any analytical relations or truths. Its province is to assist us in making available what we're already acquainted with. Oops. All right, so spin forward in time to when I was a resident a billion years ago. And I read in Scientific American this really nice article about a potential computer program that could generate content. And it would generate content based on whatever you'd feed into it. So if you fed into it Alice in Wonderland, it would generate something that sounded like Alice in Wonderland. And in this article it was called Mark V. Cheney. And the way that it worked was this. So you'd feed it in text, say 6 characters, a prompt. And it would find the most probable next character and insert it, and then move forward to the next 6 characters, using that as the prompt. So it'd find the next most probable character, et cetera, et cetera, et cetera. It doesn't think. It's just going through in a probabilistic manner and generating content based on what you feed it in. So that's Mark V. Cheney. So I was very interested about 10 years ago in kind of like deriving meaning. I mean, we have electronic health records. We have, all sorts of, we have guidelines. We have all sorts of content that we give meaning to. And I was very curious about meaning in medicine. And so I started with an idea, which is, well, what is kind of the opposite of meaning? So I went back to Mark V. Cheney, and I fed in 3 articles about 10 years ago from the Journal of Urology, and had it generate an article. And the weird thing is, if you read it, this generated article, it kind of sounds right. It has statistics, it has numbers, it talks about like VUR and things like that. But the more you try to make sense of it, the more it eludes you. There is no meaning in it. So what I wrote was, in this editorial, I realized, as in 1989 when I was a resident, that Mark V. Cheney's job was to render the comprehensible meaningless, and it does so with ruthless ease. So now we're ready to think about ChatGPT, because Mark V. Cheney is ChatGPT's ancestor. So ChatGPT works exactly like Mark V. Cheney, only instead of characters, it's whole words, phrases, sentences, paragraphs. So it's finding the next most probable thing after that. By the way, I asked, there's a image generator version of ChatGPT's large language model, and I asked it to come up with a diagram. I explained, I'm giving a talk on ChatGPT and OpenAI. Could you please draw me a picture of like how this all works? There it is. Decipher it. It's the same thing as Mark V. Cheney. It renders the comprehensible meaningless with ruthless ease. Hopefully my explanation about how ChatGPT works is a little bit more sensible. So it doesn't think like we do. And that's really important because it sounds like us, but it doesn't think like us. So I encourage you, actually, as it's freely accessible, to go in and ask it some urologic questions. Put a case in there. See what it says. And I think you'll quickly be very, very comforted to know that it's not going to replace you at any time in the near future. This is, I asked my daughter, who is a graphic designer and software engineer and an artist in her free time, to make a picture of how ChatGPT works for doctors. And I think that this is the best explanation that I could possibly come up with. And that is that it's really just a reflection of us, a very, very warped reflection of us, in which meaning is extracted. All right, so that's the don't worry about ChatGPT part. Play with ChatGPT to make yourself comfortable that it's not going to do anything that is threatening to us in the near future. What I'd like to talk about now is how we teach innovation, because I think that this is really a watershed moment in education and in innovation in general. The public out there is innovating. There are maker spaces out there that are really incredible. And so we're bringing things into the world that are extraordinary because we have the tools at this point in time. So once upon a time, in the 50s, 60s, 70s, 80s, the way that innovation worked in medicine was that an engineer and a physician would get together. The physician might write on a napkin, I'd like to do this. And the engineer would say, wow, that's great. Give me $3 million and I'll do it. And a lot of great innovation was spawned that way, but in a very inefficient manner. Likewise, engineers would build really cool things on the bench and shop them around to physicians. And, a radiologist might say, yeah, I don't think that works for me. Check out anesthesia over there, and I don't think it really works for me. Check out neurosurgery, that sort of thing. Eventually, it would land somewhere useful. Again, we got a lot of great things out of it, but very inefficient. So what's happened in the last 10 to 20 years is systems of education where the engineer learners follow around a physician, see what things the physician is frustrated at, use that for problem identification, go to the bench, prototype, test something up, bring it back to the physician, say, does this work? The physician might say, yeah, no, whatever. So this is how innovation education in biomedical engineering has been working for a bit, pretty much across the United States. It's a really wonderful thing to see. But what we and a few others have been tinkering with is to bring everyone together, just like it's done in industry. In Apple, Google, everybody's together innovating. So this is what it looks like. All of these various disciplines, medicine, engineering, business, design. Design is critical. The user perspective should be driving this whole thing. You see it in Apple, you see it in Google. This really is how modern innovation is done, and we're teaching it to budding biomedical engineers and physicians. And so we have learners of all kinds, everything from undergraduates to full professors, medical students, residents, everybody comes in. Everybody has to come up with their own problems. Everybody goes through an innovation curriculum that is similar, but everybody has their kind of own thing to do. It's very critical that you start with problem identification. So I'm going to talk a little bit about that curriculum. And as I said, it starts with problem identification. We are natural problem identifiers because we find things frustrating all the time. And once you realize that those frustrating things are actually problems that you can solve and take to the rest of the world with your solutions, then the world is your oyster. It's kind of hard to do it right, so we spend a little bit of time, 2, 3, even 4 months, finding a good problem for a learner to solve. And then we describe that problem. We come up with a problem statement that basically says, this is the problem in as technology-agnostic way as possible, and this is what a solution might look like in as technology-agnostic way as possible. So for example, flying. Flying is navigating through the air and landing safely. And the reason why we want to do that is because it's more efficient than driving, and especially during times of global stress, we need to get things quickly to a place. So that's a problem statement, without saying technology, right? Without saying, well, it needs to have wings, it needs to have a jet engine, right? That's a problem statement. And then we build a high-level specification, and in that high-level specification, you say, these are the things that it needs to solve. And then you enter into research, intellectual property research. Google Patents gives you a really easy way to do that. Existing product research, market research. If you can't figure out a value proposition in a market, you're never going to get it to the outside world. Then ideation. And one of the things that we use is solution grid brought to us from Motorola, where you put the high-level spec on the rows, the existing solutions on the columns, and figure out what works and what doesn't, and put things together in a new way. And then you prototype, and you test, and you prototype, and you test. These prototypes should be rapid, ugly, just proof of concept. And finally, when you have something that works, you secure IP. And we have these amazing tools now. We have consumer available 3D printers for relatively low cost. What you see in the middle is this thing called the Arduino, which is an embedded microcontroller, where if you want to bring smarts to your solution, you can. And then if you want to bring a real computer, Raspberry Pi, The Arduino costs about 30, 40 bucks. You can get it on Amazon. The Raspberry Pi is a full computer with a full operating system. You can get it for between 40 and 80 bucks on Amazon. This is my home. So I have a 3D printer in the office, and I have, I'm a microsurgeon, so I like to drag out things and solder small parts. But you really don't need to do that with the modern things. All you need to do is sort of plug a wire into them. This is an example of something that I made for the house. The lotionometer, it tells me when I need lotion. This is a particularly dry day in Chicago. I personally feel very sorry for my wife because these little things just litter the apartment. But I have to say, the sexiest thing that she can tell me is, Craig, I have a project for the 3D printer. All right, so this is a project, an example project of an engineering team that was doing their senior design project with us in urology. This was a smart grasper. So it would tell the user how much force they were putting on tissue. So too much, too little, that was their project. And they did a fabulous job with it. And in fact, every year we have this expo where these students in their final year of engineering show their wares. About 110, 120 teams of between 3 and 6 students. And there's a prize. And this particular innovation landed the prize over all 110, 120 projects. But when I look at this team, this is what I see. I see the future of innovation, right? Some of these engineers will go straight into industry. Some of these engineers will go into graduate school. Some of these engineers will go into medical school. So we've really accelerated the ability to do innovation by establishing a multidisciplinary innovation curriculum. And I do want to say that we are all innovators. We broke away from surgery because we used new tools. Urology, we are the innovation field in medicine. And our society has been extremely forward in building resources for us. In fact, resources that, as have been mentioned, are here at the AUA. So all of us are natural innovators. And I would encourage you to join the AUA Innovation Resources. And also, for those of you who are in academics, go over and talk to the College of Design. Go over and talk to the College of Engineering. Start a team. Have some fun. And with that, I'd like to thank you for the incredible honor of this talk.